All right. I take that as a confirmation that you guys can see my screen and my slides, and then I'm going to get started. Yeah. Hi. Thank you, BA, for the very kind words and beautiful introduction. Yeah, I'm Dheevatsa. I'm from the AI system co-design team at Facebook. I'm part of the Facebook infrastructure team, kind of dealing with what type of infrastructure that Facebook should build out, focusing on their mostly AI applications. And when we talk about AI applications, specifically at Facebook, the recommendation models have a very unique spot and very important. And we'll talk and we'll see as we go through, and I talk through some of the slides that I have, why this is important and why that's the case. Um, Before we dive into the actual the talk and the thing that I have, I wanted to kind of very quickly, briefly talk about what co-design is, right? And we call this co-design, but essentially what we try to do is trying to do this hardware design or enabling applications as a more iterative process. So far, a lot of this work, what I'm talking about as co-design has been done in multiple cases, whether it's hardware development, optimization of applications, but these have been mostly kind of independent of each other. And when we build a hardware, it gets available and we kind of try to optimize the software for this. What we've figured out, and given the type of applications are unique, and given the flexibility we are having today in terms of hardware and the scale at which these things get deployed, right? If there are innovations that can be made in hardware, they go a long way in terms of their impact and benefit. So what we try to do this as formulate this as a co-design iterative process where we go through trying to tweak the hardware for the software and then try to optimize the software on top. So that becomes an iterative process. And what I'm going to talk through today is essentially kind of a very, and this is going to be the underlying theme, because when we talk about running deep learning recommendation models, which I would assume is a very important or a very interesting topic for this audience, making sure that we are able to scale them, run them efficiently is also as important to kind of figuring out what the models do, right? So that becomes like the underlying theme for everything. So when we talk about AI applications, the AI, deep learning, all of these are used very interchangeably. It's good to kind of figure out what we mean by AI and build a taxonomy, right? At Facebook, we use AI across almost or many of our applications, whether it's web newsfeed or it's ranking or what type of video, Instagram videos that we see. All of this is some sort of AI, or even hate speech detection integrity is also driven by AI. So it encompasses a large type of application, use cases, and the different types of models driving these use cases. One key characteristic of all of these is the fact that these are deployed at a Facebook scale, right? When we deploy it on the platform, serving billions of our users which are on our platform, whatever AI application we deploy has to be thought of at that scale. Because of that scale and its requirement, this makes up a large portion of our infrastructure. What I mean by infrastructure is both the compute infrastructure in terms of our data, the hardware that we have in our data center, and also the software infrastructure, the frameworks that we build. PyTorch is a big thing that came out of Facebook and we use extensively, but everything that goes with it, right? Whether it's a data handling, data ingestion, checkpointing, all of these software infrastructure also predominantly driven by these applications. And within AI also, given that these diverse use cases, I think it's good to kind of build out a taxonomy and try to look at what type of use cases these cater to. And at Facebook, when we think about this, there are broadly two main categories, right? One, which is ranking and recommendation models or applications built out doing some sort of ranking and recommendation, which could be what comes on your news feed, what's the video, short form video ranking, or just ranking what content to show you, ads, and also search. And the other very important class are content understanding. These are things like computer vision, speech, translation, another very important class of application. And these drive very important use cases such as integrity, hate speech detection. All of these are very critical to the performance and characteristics of our platform, whereas ranking and recommendation kind of drive the core business, right? Both of these go hand in hand. But today's talk and here, I'll be talking mostly about ranking and recommendation, given these actually take a large chunk of our infrastructure. And also they have atypical requirements when it comes to content understanding and other workloads. But between these two workloads, again, this is a very broad taxonomy. right? When I talk about recommendation models, it's not just one model. And as you've seen from literature, there's a whole, I mean, it's more of a class of models. There are a whole number of variations that fall under this, starting from the wide and deep, the work that Google did, or even or factorization machines a while back, to DLR, deep learning based recommendation models. There's deep FM, there's a whole bunch of them, right? Attention FM and so on. So all of these are kind of, I put them as a class of deep learning recommendation models. And if you were to plot that along with the content understanding, which are given the type of the nature of the problem that they deal with, availability of data sets, the content understandings are a lot more. There's like standard benchmarks, like things like GPT-3, BERT, or the switch transformer. These models are kind of much more popular or studied in academia and in public. So if we look at those two and kind of use the OpenAI's total compute metric, right, which I particularly like, it's the petaflops per second base, essentially the total amount of compute a model consumes in terms of training. This captures not only the complexity of the model, but also the training data that it actually trains on. And you can see a stark difference. If I were to draw a classifier, looking at the left graph, there's clearly a difference between what DLRMs do and where content understanding models stand, right? Content understanding models are very complex. They train a large amount of data, and hence their total compute tend to be higher. DLRMs tend to be lower. And a large part of this comes from the fact that not the model themselves are complex, but they're training on a large amount of data. Given that these models typically deal with unstructured categorical data, which don't need to be curated and they could actually use data in any abstract form, they tend to deal with orders of magnitude more data, which kind of helps bring up their total compute, not the complexity. And if you look at the model themselves, the parameters, the plot on the right, you can actually see these models have already crossed the trillion parameter barrier and are pushing further ahead, right? And this kind of is the dichotomy or the unique characteristic. These are very large models, trillions of parameters, and have very low compute, which is kind of an antithesis or an atypical or an anti-pattern to what typical deep learning is. Typical deep learning is treated as dense compute, transformers, convolution, or even gems. And a lot of it, you bring a sample in and you do a lot of compute on it. Total compute goes up. Where the models themselves are large, but compared to this, they're lower. The byte to flop ratio is kind of typically lower. With DLRMs, low compute, very large models, and hence this brings in very unique characteristics when we think about training them, building infrastructure for them, and optimizing them. So when I talk about DLRMs, let's try to dive deeper and try to define what makes up a DLRM, right? So a recommendation model typically deals with all sorts of categorical features. It could be things like the pages visited or interests or likes. And this is typically represented as large embedding tables, which I'm referring to as sparse features here in this plot on the left. And they also have continuous features, which contain other characteristics, which are dense features. So essentially, it tries to take both of the categorical features, create it as a dense representation. The operation for this, essentially, you have a large embedding table, which represents this categorical feature. You do lookups based on the number of rows on them and create a dense representation, which becomes a representation for that categorical feature, and then combine and then infer on this through the top and bottom neural networks, right? This is a very rough overview or a schematic of the key components of a recommendation model. I'm overly simplifying it here to capture the key components, not go into details. And each of these components, right, whether it's the embedding lookup or this feature generation, the neural networks, I'm just calling them bottom and top neural networks, or the feature interaction, all of these have a lot of sophistication in themselves and variation. So you could do a lot of different things at each of these levels, and depending on the tasks that they're catering to and the models being built for. But at a very high level, if you take like a 10 million foot view, you can actually see these as the 4 components. And why we capture these as 4 components, you'll see later, because it helps us to kind of characterize these models better. And the plot on the right, I like using, and this is basically kind of normalized number of racks, which we had in a previous paper, which shows the importance or kind of the position that these models hold. These are essentially, the plot shows the number of racks normalized by a kind of total metric. And if you look at it, all of the other models take about 50%, and there's a recommendation model single-handedly contribute to about 50%. And this is up to 2020, 2019, late 2019, because this is from a 2020, and this trend hasn't gone away. And it continues to stay that way. So this kind of indicates the importance and why there's a lot of focus on recommendation models. And it's understandably so, right? I mean, I'm sure a lot of the people in the audience here would be able to see, just because recommendation models are quite abstract, and the type of tasks and work that they're able to do is still very abstract, making them very popular. Now, if we were to go back and we've kind of built out a schematic of what these recommendation models are. And now let's try to understand what it takes to train them and where the atypicalness of their characteristic kind of plays up and what the challenges are. We keep talking about training deep learning models, and there's a lot of work training typical content understanding models. But when we think about the deep learning recommendation models, coming from the fact that, again, the two key things that I mentioned, they're very large, terabytes in terms of model size, training on petabytes of data, and typically lower compute intensity. And when we try to train these at scale, given that we want to be able to train much faster and train through these large amounts of data with high throughput, it becomes a HPC or a supercomputing type of a problem, right? And the reason I kind of call it HPC, it also comes from my previous kind of life where I was looking at HPC and supercomputing applications, because these were driving large scale compute requirements. But since the past 5 or so years, it's mostly been deep learning applications which have been taking kind of the cut and driving such requirements. And if you look at this, these are also very high performance computing applications, right? It's not just compute. It requires optimizing all components of our underlying hardware to make sure that we can actually train these models effectively and as fast as possible, right? It needs memory. We need to be able to accommodate these large embeddings in terms of capacity, and also it needs bandwidth, because we need to make sure that when we're doing embedding lookups, we have sufficient memory bandwidth. And more important than other cases, it also needs a lot of I/O and network. Because of the size of these models, they cannot be fed on a single node. Distributed training is a necessity just to get to train these models of any practical interest. And when we start about training, it's not about the distributed training in the conventional sense, and we'll talk a little bit more about it, not just data parallel. The model sizes are so large, even the model needs to be sharded or parallelized, hence giving rise to more complicated communication patterns and higher compute requirements. All of this put together, this needs to be deployed not in a supercomputer, although this is an HPC type of an application, but within data centers. And it's not one application you run at complete scale and you kind of run it as fast as possible. This has to be done day in and day out, where hundreds of these models are being trained continually on different tasks, different data. So it kind of is requirements which are very high from all perspectives. Single model has a lot of requirements, it needs to scale, and the way these are used is extremely challenging and needs to kind of the infrastructure to be able to support this. So just to recap, what does it take to actually train high performance scalable trail? DLRMs, they're different. They present unique challenges. The sheer size of the model and their compute characteristics require them to be different. And we need to think about beyond what we do for distributed training of conventional models to be able to support these efficiently. And given their compute intensity, it's not all about gems or matrix multiplies or dense compute, right? Not fully connected layers, not the convolutional layers, but we need to pay a lot of attention to embedding. I'm going to classify these as kind of broad embedding operators, which involve the embedding lookup, embedding update, the optimizer updates, and everything that goes with it, which we will see has a lot of challenges and unique opportunities. And given that these models are used in different use cases, I briefly touched upon the continual training, which essentially is an online training use case. These models are trained on a large amount of data that are available offline, and they're deployed on a platform, whether to our newsfeed, and they continually get trained again and again. So whatever we think of as a solution or a high performance solution needs to cater to both of these use cases. And to top it all off, we have very smart and kind of people looking at these models because these are important use cases, and these models are constantly evolving and changing rapidly. So whenever we think of supporting such use cases and from the infrastructure point of view, it becomes extremely challenging, and it kind of makes us to rethink what AI training or distributed training at scale is. So I've been talking about parallelism and the scale and how this is different, right? Let's kind of dig a little bit deeper to understand. When we think about parallelism, although some of these language models, the larger models, are looking at model parallelism, it's primarily model parallelism to specific that model context, and it's mostly data parallelism. And it's understandable given that the models are smaller. When we do data parallelism and when we have a large amount of samples to train these on, you would want to distribute the samples and replicate the model. This has inherent benefits such as reduced communication, and you actually get to train much faster and go through your data. But given DLRMs are so large, this is kind of prohibitive, right? We can't expect to take a terabyte model or several terabytes of model itself and replicate on each node, let alone accommodating on a single kind of compute node or a compute device. So this kind of becomes, we have to go about it more holistically, and we have to think about how do we go about doing this. And if you go back to the top right, this is that schematic of DLRMs. It's not the same everywhere, right? The sparse embeddings or the sparse features are very large. We would want to think about thinking about it in different ways or unique ways to parallelize. But the top and bottom MLPs, these are conventional convolution layers, ResNet layers. Think about them as regular deep learning models that we are all familiar with on the content understanding side. For these, doing model parallelism is not beneficial. So we need to think about it more holistically, combine model where applicable, data parallelism where applicable, and still retain those benefits, and pipeline parallelism. So it's kind of, in my view, I see this as the true distributed training where we're thinking about it in all possible ways, whether it's pipeline, model, and data. And even with model parallelism, it's about how we think about model parallelism, right? When we say model parallelism, it's not just one, take the parameters and distribute. It's not just that. We have to go back and look at what it entails. The model that we're actually splitting are number of tables. If you look at these models, they have hundreds, if not thousands of such tables. And these tables are huge. Each table can be like several tens of gigabytes. So we're actually having large number of tables with the tables being very large. So you can think about this as like a 3D tensor. And when we kind of partition this goes back to going back to the HPC or the scientific computing domain, you can think about this as kind of a domain decomposition. You can either go horizontally, split them row-wise, or vertically column-wise, or kind of take each table and split them across. To add more variety to this mix, not all tables are large. Even within those thousands of tables, there's a very skewed characteristics. There are a lot of very small tables, and there are a few very large tables which contribute to a majority of the overheads, right? So for the smaller tables, actually parallelizing them, what we do with the larger ones, is not efficient. So we would want to go back to the data parallel case and say, look, for tables which are small, we need to be able to replicate. So essentially, use all the tools that we have available in terms of techniques and kind of merge them all together and think about this more holistically. We call this 4D model parallelism. Essentially, all of these dimensions, and it's not just one level, right? And you would want to take this and say, if you have a platform such as a DGX node and several such DGX nodes connected together, which is typically, if you were training on a GPU-based platform, you can think of a hierarchical setup. What you would do within a node is very different what you do across nodes. So you can actually combine these strategies on multiple levels. And this becomes kind of a very different space as opposed to distributed training, where we're thinking about, we take the large last embedding, do the model parallelism, and the rest, everything is data parallelism. This is more kind of intrusive and elaborate in the way we think about parallelism. And this is essentially necessary and a requirement to be able to train efficiently. And the second, the other kind of the key characteristic or a difference are, maybe I'm not going to spend a lot of time on talking about MLPs or the actual neural networks. These are typical part of standard libraries like cuDNN or MKLDNN, and they've been optimized, right? Convolutions, GEM, there's a lot of work gone into actually optimizing them. But where there's a gap is essentially these embedding operators. As we saw, embeddings are very important. They're a critical part of these models, and they have very different or unique characteristics. These are memory bound, bandwidth intensive, and optimizing them needs to be thought about differently because they don't play to the strengths of accelerators such as GPU, right? GPUs do have high bandwidth memory, and those can be kind of leveraged. But when you think about GPUs, it's a tensor core, high compute intensive or dense compute, which actually leverage from them. But kind of trying to formulate these kernels or implementations to be able to leverage still the GPUs when we have lower arithmetic intensity and leverage the high bandwidth is a kind of a gap or something that we need to additionally do to make sure that we get performance in these models, right? So we optimized implementation for embedding. It's not, it's not mainstream part of these libraries, hoping that with DLRM becoming more popular, there's a lot of effort from companies such as Alibaba, Tencent, and Facebook, and we would try to have DLRM as part of MLPerf so that there is more visibility from vendors. With this, we're hoping embedding or such operators also start becoming mainstream. But without that, we're kind of dead in the water and we don't get performance, right? So having efficient implementation for these are very important. And optimizing these, other than the fact that optimizing for bandwidth, another key consideration here is when we think about this, there are thousands of such embedding or up to thousands of such tables, right? If you were to naively think about each of them being a kernel call, just the latency for launching these kernels on things like GPU become significant overheads, right? So there are when we think about even fusion and how we fuse the kernels and even in the backward pass, given that we want to limit the bandwidth or the number of passes to memory, we have to think about more efficient ways of fusion. All of these are techniques that kind of haven't been explored or are necessary for deep learning recommendation models. I'm going to present some of the results from the recent work that we put out. And to achieve this, the implementations that we have, we've actually open source, staying with kind of the open source spirit of what everything that Facebook does. We actually have these implementation, and we invite the community here also to kind of take a look, contribute, and extend these. Right? So we have few. These are important, and as the plots here on the right actually showcase the achieved bandwidth on kind of latest generation GPUs. Right? With efficient optimizations, we're able to saturate majority of the bandwidth, but it takes a lot of thought and difference and unique innovations to get there. So far, I've been talking mostly about the software parts of it. I do want, given that I started off saying hardware co-design, I just wanted to step back and spend a couple of minutes on talking about the hardware. To enable such software and such unique application, I think we need to go back, take a look at how we think about as hardware platforms. We do have several popular hardware platforms. I'm going to pick DGX, the NVIDIA DGX, given that it's out there and it's used. And again, what it was designed for was CU type applications, right? Huge injection bandwidth, capable of supporting all reduced, thinking about data parallelism. But when we think about cases such as DLRMs, which not only require injection, also think about bisection bandwidth, because we need to support the all-to-all coming from model parallelism or the many-to-many, one-to-many, and all different types of communication patterns. We need to think about how this fits. And also, if you're deploying in data centers, we need to make sure that there is capability that we can add, and it's compatible with existing data center infrastructure. Towards this end, Facebook has this tradition of building hardware or kind of contributing back to the open source through open compute platform. And we did talk about the Xeon platform in 2019, which was kind of designed as a super node to cater to these models. But the rapid growth of these models kind of required us to rethink that platform and come up with Xeon EX, or the improvement, which is essentially an extensible form of Xeon platform, which we will be contributing back to OCP, which we can use to build data centers, right? It's essentially taking all the goodness of the Xeon platform, making it scalable and extensible so that we can build clusters, training clusters, or supercomputer type machines within data centers and use it for such applications. So it's not only content understanding, but also caters to the deep learning recommendation model requirements. So I'm going to just flash some of the results. All of this is on in our recent paper that we put out on arXiv, and I'm happy to go through more details. But given this is more to just mention all of the optimization that I talked about, whether it's the embeddings or this hardware, all of these put together, or the sharding or the 4D parallelism, allows us to get to kind of state-of-the-art performance. Using it in our production case, we've seen almost orders of magnitude, right? Up to 100x speed up on production models. And when we talk about production models, and again, it becomes a little bit, there are no standard benchmarks. So it's a kind of tricky to go back and say it improved 100x over a standard benchmark. What I can say is, look, we had X in production, we deployed this with new models increasing, and we still see a huge improvement. And these are deployed in production again, right? And this, we can see those improvement and kind of benefits coming in. And the type of improvements comes from all of these optimizations. Sharding providing a huge boost, embeddings, implementations, not just the optimized implementation, but using lower precision, and making sure that when we scale, we quantize communication. And the quantized comms was another paper we actually talked about as we were working through at last year at DLP. Now it's kind of been at production. It's part of our Xeon EX-based DLRM system, and we've been able to kind of leverage this in production. So looking ahead, I think I just wanted to kind of lead this audience with this thinking. We need to kind of look at, we all know, I'm not going to make the case for recommendation model. I think at KDD, we all know the importance of recommendation models. And we've been looking, I mean, this group has been looking at it for a while. But just the nature of more complex demanding models are not going away. It's recommendation models. It could be new class of models coming. And when we think about this, we have to not think about when we build those models independently and just the model view, but we have to think about more as a hardware software co-design approach, where we think about how we build infrastructure, how we can leverage infrastructure to run these models. Because if we build a very fancy model which we can run on the existing infrastructure, that becomes kind of a catch-22. So we have to think about it more holistically in a joint way. And given these requirements, and we need to go beyond current standard systems and start looking at specialized systems. With this, I'm going to pause. I think I ran through my 30 minutes. We do have, I was told that we have like about 10 to 15 minutes for questions. I'm happy to go through questions. And on this slide, I've left a few of the references that I've actually talked about or alluded to in my talk, papers from our group and our collaborators, which are all of which mostly are on archive. And I would welcome everyone to take a look. And if there's any questions or follow-ups, I'm happy to do that offline too. Right.